Hi everyone, my name is Benjamin Terrian and I'll be presenting Parametric Scattering Networks, joint work with my co-authors here. What is scattering, you may ask? The scattering transform computes a representation of an input signal X with geometric invariance and deformation stability. In this work, we focus on networks that compute the scattering transform of 2D signals, i.e. images, called scattering convolutional networks, which are depicted by the figure here. These networks cascade wavelet transforms, complex modulus nonlinearities, and low-pass filters. They compute a number of scattering coefficients that are concatenated to obtain the scattering representation. These coefficients correspond to black nodes in the tree, seen here. The zeroth order scattering coefficients are computed by convolving the input signal X with a low-pass filter phi. The first order scattering coefficients are computed by convolving the input signal with complex wavelets psi, taking the pointwise complex modulus, and finally applying a low-pass filter phi. Subsequent orders are computed by further cascading these operations. Let us now situate our contribution within the existing literature. Scattering networks were introduced by Stéphane Malat in his seminal work, Group Invariant Scattering, seen here, which established many mathematical properties of the scattering transform. In subsequent years, scattering transforms were studied for computing representations of 2D, 1D, and 3D signals, followed by geometric scattering, a more recent extension of scattering to non-Euclidean geometries. None of these works incorporate learning, however. In contrast, hybrid 2D scattering proposed fusing the scattering transform with learnable processing layers, showing that concatenating a ResNet on top of a scattering convolutional network can obtain reasonable performance on ImageNet. Our work continues down this learning path and is part of a recent trend that learns the parameters of wavelets in the scattering transform. Our work focuses on 2D signals, whereas concurrent work proposes similar extensions to 1D and geometric settings. Traditionally, the wavelet filters in the scattering transform are created by carefully rotating and dilating a mother wavelet to ensure the resulting filter bank forms an efficient tight frame. The black border figures shown here show this traditional construction. We see that the wavelets only cover half of the frequency plane due to symmetry. Each wavelet is shown with a white outline around it. In our parametric scattering networks, we relax the standard construction, seen here, shedding light on its optimality. The figures with colorful boundaries show the filter banks optimized over different data sets, showing our relaxation of this construction. We note that the blue outline filters optimized for object recognition and red outline filters optimized for X-ray diagnosis become thinner and more orientation selective in Fourier space, possibly selecting out edges, while the wavelets optimized for textures become wider and less orientation selective, throwing away that edge information, which is not useful for discriminating textures. The datasets that we used to optimize these filters were CFAR10, the 10 class natural image dataset, COVIDX CRX2, a dataset of X-ray images labeled positive or negative, and KTH-TIPS2, a texture dataset of 11 materials. Here's a video of the filters being optimized over 500 epochs of training on a small number of samples from each of these datasets. We see that they obtain the parametrizations we saw in the previous slide. Since we optimize the parameters of Morley wavelet equations, these equations impose a parametric prior on our networks, biasing them towards a favorable solution, which shines in small data settings. Here we show improvements in green of our learned scattering over the same networks with a traditional tight frame construction. On every dataset in every setting, we improve over the tight frame constructed network. This suggests that tight frame is not optimal for many problems of interest. We'd like to thank and acknowledge our funding agencies and academic institutions, as this work would not have been possible without them. Thank you. Finally, thank you all for attending the talk virtually. If you are interested in using parametric scattering in your own work, or simply exploring scattering networks, we have included QR code links to our parametric scattering repository and Kimasio, an efficient open source implementation of the scattering transform. So I invite you all to check them out. Thank you.